Welcome back, folks. We are now in section 3.3 for elementary statistics, which gets into measures of relative standing and box plots. Ooh. So now the first part of this actually connects pretty well to what we just finished in 3.2. So remember, we were looking at Chebyshev's and the empirical rule, and just looking at how the number of standard deviations away is important for determining the percentage of data between cutoffs above and below the mean. What we're looking at here for this first part is going to build off of that a little bit, and we're actually looking at how we can identify exactly how many standard deviations a value is away from the mean. So it might be a fraction of a number of standard deviations versus just a whole number like 2 or 3 or 1. So let's see what that looks like. So now that we have, now that we can find the sample standard deviation for sets of data, let's examine how these values relate to the measures of variation. Using the mean and standard deviation, we can precisely determine how far a given value is from the mean standard deviation wise. Okay, so how does it work? Well, we have a formula, always. A z-score, or a standardized value, is the number of standard deviations that a given value x is above or below the mean. The z-score is calculated using one of the following. So we have our sample formula, and we have our population one. So in this case, x is the actual value we're analyzing. We want to make some determination about it. X bar is our mean, S is our standard deviation, and then we have the comparable formula for the population. So very quick formula. The most important thing about it, though, for our purposes, we are always going to round it to 2 decimal places. So not 1, not 3. Specifically, it's got to be 2. So, and just another version of describing how this works. Basically, a z-score is simply a number that corresponds to the number of standard deviations that a value x is away from the mean. So, for example, if we have z is equal to 1.26 for a given value of x, then x is 1.26 standard deviations above the mean. So what if we had a different value of x and the z-score for it was negative 0.87? What could we say about x then? Well, very similar to what we have up here, we should be able to say that x is 0.87 standard deviations below the mean. So all because of that negative sign, that automatically tells us that it's got to be below the mean. And again, that 0.87 is just a number of standard deviations away. All right. So let's put it into a problem and see what we can figure out here. So in 2012, the Oscar-winning Best Actress was Helen Mirren, who was 61 at the time of the award. The Oscar-winning Best Actresses have a mean age of 35.8 years and a standard deviation of 11.3 years. Okay, so they did all the math for us. Yay! What is the difference between Helen Mirren's age and the mean age? So this is kind of what we did back at the end of section 3.2. We said, okay, well, we have these 2 cutoffs. We wanted to first confirm that the mean was in the middle, so we had to do some subtraction on each side and get that value and show that it was the same. So that's kind of what we're doing here. We're just subtracting those 2 values. So 61 minus 35.8, which better be 25.2 years. Okay, so that's quick. So that's kind of like that distance on either side. But what did we do with it? Well, we had to determine if it was 1, 2, or 3 standard deviations, and we did that based on what the original standard deviation was. We just said, okay, this is a multiplier of that, and it was quick to tell because the math was easy. But in this case, it's not so easy to determine precisely unless we just divide it. So the next step is to divide that 25.2 by the 11.3. So 11.3 was the standard deviation. So we just want to see how many times it goes in. And if I recall correctly, it's a long decimal, 2.230088 dot dot dot, and it just keeps going. Now, if we kind of go back to what we had said before, this is kind of like a z-score, so let's round it off to 2 decimal places. So 2.23. All right. And so now, what's the difference between doing these 2 steps and what they want in step C? Convert Helen Mirren's age to a z-score. Well, so all we're doing is just presenting it a slightly different way. So we got our x minus our mean all over standard deviation. So it's exactly the same thing, but it's just in one compact formula. So we're going to get the same exact answer. Now, technically, this is a number of standard deviations. Now, on the first one, they explicitly say it's standard deviation. So we should just kind of, itemize that or note that. But for z-scores in general, they do not have units. So no units on z-scores. So don't feel you have to put any kind of units on there. All right, now the interesting question. D. If we consider significant ages to be those that convert to z-scores between -2 and +2, is Helen Mirren's age significantly low, significantly high, or not significant? So, well, how does this value of 2.23 compare to those cutoffs? That's what we really want to know. Well, we should be able to see that it's bigger than 2. And because it's bigger than 2, that puts it way up on the high range of values. So this will be significantly high. Cheap lead. So we can say it in a quick, explanation. So it is significantly high, and it's because 2.23 is greater than our maximum value. So as soon as you're greater than that maximum value, you're in the significantly higher range. If you're lower than the lowest, if it was below -2, then it would be significantly low. And anything in between has to be not significant. So, and we can see this on the next page. So we have our z-scores and significant values. So exactly how I explained it. So when z is less than or equal to -2, it's significantly low. If z is greater than or equal to 2, then it's significantly high. And if it's strictly in between -2 and 2, then it's not significant. And we can kind of see the graphic here as well. That looks pretty. Now, this is an old graphic, so it's got usual, unusual, and ordinary in there. But we use more up-to-date terms as far as significant, not significant, significantly low, significantly high. So just keep that in mind. Some textbooks use that same terminology, unusual and ordinary or usual. So they all mean the same thing. So, okay. The last note, whenever a data value is less than the mean, its corresponding z-score must be negative. So again, below the mean, negative z-scores. All right, let's try one more example that encompasses this, and then we'll pause and jump into a new video. So example 2 says scores on the SAT test have a mean of 1518 and a standard deviation of 325. Scores on the ACT test have a mean of 21.1 and a standard deviation of 4.8. Which is relatively better, a score of 1840 on the SAT test or a score of 26.0 on the ACT test, and why? Well, let's try to summarize our information, and then we'll go from there. So we have our SAT stuff, which shows we have a mean of 1518, standard deviation of 325, and they want us to look at a value of 1840. So that is our value of x. Okay, ACT. Our mean is 21.1. Standard deviation is 4.8. And now, for this one, they're looking at a specific value of 26.0. So that's our value of x for that scenario. So, now what? Well, you can kind of guess that we're going to be looking at z-scores, but we're still not quite sure what we're going to do with them. But let's find them anyways and see what happens. So if we get the z-score for the first case, so again, the values first, minus the mean, all over standard deviation. So let's get our calculator out here. Now again, be careful how you put this in. Do not try to put that all into your calculator in one swoop. It won't do it right. So if I said 1840 minus 1518 divided by 325, I get that. 1,835.32, which is not right. It's way too big. But if you do it in 2 steps, so do the subtraction, then hit equals, and then divide it by 325, we get a different answer. So it's hard to see, but 0.9907, blah, blah. So let's round it to 2 places to 0.99. Okay, so there's that one. Now let's do the other one. So we got 26.0 minus 21.1 all over 4.8. Let's see what that gives us. Minus 21.1 equals divided by 4.8. 1.0208, so again, 2 places, so 1.02. All right, so that's interesting, but what does that tell us? What's the question? Which is relatively better, a score of 1840 on the SAT or 26.0 on the ACT, and why? Well, let's think about this. If you're doing well on a test, do you want to be close to the average, or do you want to surpass the average and be on the high end as far away from the mean as you possibly can? Well, hopefully you're saying you want to be far away. You want to be far away on the good side, not on the bad side. So just keep that straight. So out of these two, which one's further away from its mean? Well, the 1.02 is a little bit further away, not much, but a little bit further away on the good side from the mean. So this would tell me that 26.0 is better. Well, I'll try to be a little bit more explicit with my sentence here. It's better than 1840 because its z-score is greater. Again, you could try to be a little bit more descriptive than that, but hopefully you get the idea of where I'm coming from. So, okay, well that wraps up the z-score concept. And again, that's more of a tie-in to 3.2, but we're going to see the z-score stuff again. Don't think this is a one-time thing. We're definitely going to see this more. So, all right, so we'll continue into percentiles in the next video, so we'll see you in a sec.